Hello, welcome to Physics with Ben. Don't forget to subscribe, like, comment, and share this video to those that need it. Before you hear is alternative to practicals, alternative D. This video is proudly sponsored and powered by one of my Liberian friend. He asked me to make this video for his people that they are writing WAEC, alternative WAEC practicals very soon in this year. It is also a great privilege and an honor that my video has gotten much recognition outside Nigeria, and I pray that this video will achieve the purpose with which it is made for. I wish you guys success in your exams over there. And if you're also watching, you are not a Liberian, a Nigerian, this video will also help you. We in Nigeria, we make use of alternative A. They over there, they make use of alternative D. So this is alternative D. You may love to click in the description box below to get the theory and the calculations on meter bridge, Wheatstone bridge, and all the theories on current, electricity, and also Ohm's law. My Liberian friend, you have done me a great favor. Thank you for giving me this privilege. I will never take this for granted. It is an honor. I am so delighted. Thank you and remain blessed. Without wasting much time, let us go straight to the point. If you have been watching my videos on alternative to practicals, which is alternative A, which I always do, the difference, there's no difference. It is the same thing. The only thing here is the question is not the same, but the pattern is still the same. So the other videos you have watched and this one, the message is still the same thing. Well, without wasting much time, let us go straight to the point. I read. So before we proceed, the materials needed for this experiment, you need a calculator, a transparent 30 cm ruler. You also need WAEC standard graph sheets. This is the graph sheet I'm using for this experiment. You need an eraser and also a pencil. Because I'm a teacher, I'm going to make use of this pen so that the video, the writings will be very clear. So without wasting much time, let us go straight to the point. I read. The diagram above shows a meter bridge circuit containing a resistance wire in the left-hand gap and a fixed resistor R in the right side. A crocodile clip is used to tap a length Y of the resistance wire in the circuit, and the jockey is used to determine the balance point C. The balance length X is equal to CB is measured and recorded. The procedure is repeated for four other lengths Y of the resistance wire. Figure 3A shows the length Y subscript I, while figure 3B shows the corresponding balance length X subscript I, where I is equal to 1, 2, 3, 4, and 5 respectively. Measure and record the values Y subscript I. Use the scale provided to convert the values Y subscript I to real values. Measure and record the values xi. Use the scale provided to convert the values xi to real values capital X. Ignore the tickings here. I was studying the question and I did all these things. Use the scale provided to convert the values xi to real values of capital Xi. Evaluate z is equal to 100 minus bracket 100 minus x over z, and t is equal to 10 over y in each case. Tabulate your results. Plot a graph of x over a graph with x over z on the vertical axis and t on the horizontal axis. Determine the slope s of the graph. Given that s is equal to a all over p, where a is equal to 5.31 exponential negative 4 cm squared, calculate p. State two precautions that are necessary to ensure accurate results when performing the experiment in the laboratory. Draw a graph to show the relationship between the resistance and the temperature of a light-dependent resistor. And here they ask us to find the equivalent resistance in the circuits. Or you may love to screenshot this question so that you can study it on your own. So this is diagram figure 3, figure 3a and figure 3b. So as I've been doing in the other videos, the first things first in every experiment, be it practical, the real practical or alternative to practical, is your table of values. So we are going to plot a graph of we're not going to plot a quadratic graph, so we ignore this. We're going to plot a linear graph. So we're going to plot a graph with x. Let's set up a graph with x all over z versus what? T. Versus t. And then here we have x all over z axis and then the t axis. So the first things first we are going to do is to generate our table of values. I told us that our table of values carries the highest mark in every experiment. So we write that our observations or table of values. Good. If you go through the question, the experiment was run the first time and all four other times. So it means that the experiment was performed 5 consecutive times. So write that our serial number, we have 1, we have 2, we have 3, we have 4, we have 5. That also corresponds with I is equal to 1, 2, 3, 4, 5, meaning the experiment was performed 5 times. These are the things you take note of. So the composite parameters in the experiment, they ask us to measure y. Y is the first composite parameter. So we draw a straight line here, straight down. Good. And then we'll have small y, I, and I is measured in cm, so slash cm. And then you draw a straight line down here again. The second composite parameter, they ask us to use the scale provided to convert yi to real values of y, capital Yi. So we'll have capital Y here, I slash cm. We draw a straight line. Good. The next composite parameter, you need to make your table of values right because it carries the highest mark. Carries the highest mark in every experiment. The next one, say measure and record the values x. That is the balance point. X is this. Here, this is the y. So we have xi slash cm as the next composite parameter. You draw a straight line down here. And then they also ask us to they ask us to also convert this to real values of this. So we'll write that here is our capital Xi, then slash cm. We draw a straight line. Good. They also ask us to evaluate z is equals to bracket 100 minus x bracket close. So our z is equals to, you don't need to write this equation, but I'm just doing for sake of clarity. Let me just write just z into 100 minus x bracket close, and the unit is also cm. You draw a straight line. Sorry, the next composite parameter is x over z. We have x over z. X over z has no units because cm cancels out cm, so there's no need for that. The next composite parameter is t. Your t is 10 all over y. Of course, your t is cm inverse. So these are your composite parameters. Your table of values must appear exactly the way it is here right now. So the next thing to do is to perform, is to do the alternative to practicals. Without wasting more time, the controlled variables in this experiment, this is a standard resistor, is fixed. The length of the wire is varied. Remember that the increase in the length of the wire will cause the temperature, will cause the resistance of the wire to increase. This is what is also achieved in this experiment. And also the balance points, balance length CB, will also be changing throughout the experiment. So we're going to verify in this experiment if y and the type of relationship that exists between x, y, and x. Is it a direct relationship or an inverse relationship? So this is the measurements for y and x. So this is the ruler we are going to use in this experiment. The calibration of this ruler is from 0 cm to 30 cm. You must always use a transparent 30 centimeter ruler because this is the one that is recommended for experiment in physics. If you use an opaque one, you may not be able to see some of the values when you are plotting, some of the points when you are plotting the graph. So let's go straight to the points. So I'm going to place the zero end here, and then the other length here. Yeah, if you observe critically, the value there is 3. This is 5, 1, 2, 3 is 5.3. So we record 5.30, not just 5.3. We record everything here to 2 decimal places, while this and this to 3 decimal places. So the next is y2, which is this point here. Y2, the value for y2 is exactly 7. You can see that this is 7. And so we write 7.00. The value for y3 is 8. This is 7. This is 8.4. So we'll write 8.40. Good. And then for y3, for y4 we have this is 10, 10.123, 10.3. We have 10.30, and then for y5 we have this is 11, 11.5.6.7.8, 11.8, 11.80. Good. We are done with the values of y, and then let's go straight to the values of x. Before we go to the value of x, let's convert these values first. In converting the values of small y to real y, this is the scale. 1 cm is to 5 centimeter. So what this means that 1 cm is to 5 cm. So 5.3 cm is to what? X cm. So you cross multiply, and when you do that, that means we're going to multiply everything here by 5 cm. So I would say this is 5.3 times 5, and that will give me 26.50. 7 times 5, that will give me 35.500. And so this is what we have. This times 5 we got this, times 5 we got this times 5 we got this times 5 we got this. So these are the real values, what you will get if you are performing the experiment in the laboratory. This is the real value, and these are the scale value. So move straight to find these particular values now. X1, the balance length. So for when it was Y1, X1 was what? So we measure X1. Our X1 is exactly 10.1. So write 10.10. Then our X2 is exactly 9.5. So write 9.50. And our X3 is exactly 8.9, 8.95. So write 8.995. And X4, this is 8.25. We have 8.25. And then our X5, this is 7, is 7.5.6.7.8, is a 7.80. So these are the readings for XI. So we have to convert this to, let's look at what they have for us for here. So one scale is to 5 cm. So if one scale is to 5 cm, the first value here, 10.10, is to X cm. So you cross multiply. So this means that every value here times 5 is a result. So we say 10.1 times 5, we got 50.50. And 9.5 times 5, we got 47.550. And so we are done with the conversion. These are the real values. So the next thing is to evaluate for Z, X, and T. Z is 100 minus this, everything 100 minus this column, put the result here. So we have 100 minus 10.1. We have 89.90. We have 100 minus 9.5. We have 90.50. And so we are done with this. The next is X over Z. Remember, I told you in the other videos that anytime you have any composite parameter, x squared, root x, the cube root of x, or 1 over x, you record that to at least 3 decimal places. So we're going to record this column and this column to 3 decimal places. So our X over Z simply means this value divided by this, you put the result here. So we have 10.1 divided by 89.9. We got 0 0.11 and 2. So we have 9.5 divided by 90.5. We got 0.10. We round it up 105. And so we are done getting the values for x over z. The next is t. 10 divided by these values here. 10 divided by 3.5, put the result. 10 divided by 7, put the result here. So we'll have 10 divided by 5.3. We got, let me do that again. 10 divided by 5.3. We got 1.88, and then you round it up 887. We have 10 divided by 7. We got 1.429. Round it up 9. And so we are done with our observations or table of values. This is exactly how your table of values will look like if you are given anything related to it. Don't forget, this is a past question. I don't know which year is this, but what you will see in this year's question, if it is on electricity or whatever type of whatever you are given to measure, this is the pattern you are going to follow. And you're going to get things done straight. Don't forget that this carries the highest marks. So the next thing to do, we are done with this. We are done with this. We are also done with this. We are done with this. Right now, we are on this point. We have to plot the graph of this x over z on the vertical axis and t on the horizontal axis. So before we plot the graph, let us look at what I call the trend of the experiment. The trend of every experiment is very, very, very important. The trend shows the relationship, the parameters, the controlled or the constant parameters in the experiment, the relationship they share with each other. It could be a direct relationship or an inverse relationship, meaning if it is a direct relationship, one parameter is increasing, the other parameter is increasing. One parameter is decreasing, the other parameter is decreasing. In an inverse relationship, one parameter is increasing, the other is decreasing. One parameter is decreasing, the other is increasing. So let's check the original trend of this experiment. We have here as y is increasing from 5 to 11, x is decreasing from 10 to 11. Yes, that is the length of the resistance wire as it was increasing, the length of the balance point was also decreasing. Increase, decrease. So we say that, and if we look at also the converted real values, we have 26 down to, has increased down to 59, and 50 decreased down to 39. So we say that yi is inversely proportional to xi. That is the relationship that they share with each other. And if you plot such a graph, the graph will look like this. The graph of this against this or this against this, the graph will look like this. Now let's look at the customized trend. This is what the examiners asked us to plot. The graph of this on the everything here on the y-axis and everything here on the x-axis. So we have 0.112 has decreased down to 0.085. We have 1.88 has decreased down to 0.847. So this and this will have decrease, decrease. The trend for this customized values column here is decrease, decrease. And in a decrease, decrease or increase, increase trend, that is to say that x all over z is directly proportional to t. If you plot such a graph of x over z or t over z, this is what I predict you are going to have. A straight line graph with an intercept on the y-axis, that is a graph of y is equals to mx plus c, or a graph passing through the origin with no intercepts, that is a y is equals to mx, and then the graph passing through here having intercepts on the horizontal axis and on the negative y-axis. So these are the graph I predicted for this experiment. We may get any of these three: graph 1, graph 2, graph 3. The reason why you need to know this is that it gives you an edge over the experiment. You foresee what will happen in your experiment and also guides you. Now, the next thing we are going to do is to find a suitable scale for this graph. These are decimal scales, decimal values, and the scale for decimal values are somehow difficult to get, but with the videos I've been producing here, you can see that they are very, very simple to come by with. So for these values, let us say that 0.04 cm to represent 4 units. So we say that here is 0.044 cm to 4, sorry, units to let's say unit here, unit to 4 cm, and here we say that we have 0.4 unit to also 4 cm. This is a YX standard graph. From here to here, from here to here is 1 cm, and from here to here is 2 cm. So this is 3, this is 2 cm, this is 4 cm. So we mean that each time you increase, that is this 0.04 plus 0.04 plus 0.04 in that order. So we're gonna draw the first line, which is our horizontal line. Good. You put an arrow to indicate the direction of your graph, and this is t. Our t, the unit is per cm. You must put a unit, it carries half mark. And then we also draw the vertical line here. Good. And this is 0, 0, 0. And then you put an arrow here, and this is x over z. This is half mark, and also this is half mark, as is labeled correctly. So we said 0.04 unit to 4 cm. So this is 2 cm, this is 4 cm. So we write 0.04 here. So the next one is here. 0.04 plus 0.04 give you 0.08. The next one will be 0.048 plus 0.04, and that will give us 0.12. 0.12 plus 0.04, that will give us 0.16. and 0.16 plus 0.04, that will give us 0.2. If you can look at the graph, the highest value here is 0.1, and then we have 0.2. It means that this value and this last value, they are all represented in this scale of the graph. On the horizontal axis, we say that let's 0.4 units to represent 4 cm. So and this is our 4 cm, this is 4 cm here, another 4 cm is here. What am I trying to say? Sorry, this is 2 cm, this is 4 cm, another 4 cm, another 4 cm, another 4 cm, and then another 4 cm. So this is 0.4 plus 0.4 will give you 0.8. 0.8 plus 0.4 will give you 1.2. 1.2 plus 0.4 will give you 1.6. 1.6 plus 0.4 will give you 2. And so this value is 2. Let me write it somewhere here or somewhere up here. And so we are done with this. And then the next thing is to find the value for each small box. The value for each small box is very, very important in every experiment. It helps you to get the exact values, and also gives you precision while dealing with your graph. So we'd say that 0.4 on this axis, 0.4 divided by 1, 2, 3, 4, 5, 20 small boxes. This is 10, this is 20. So we say that 0.4 divided by 20, and that will give us 0.02. So on this axis, 0.02 is the value for each small box. Going this way, what do we have? We say that 0.04 divided by the same 20. 0.04 divided by 20, and that will give us 0.04, 0.0, sorry, 0.0, 0.04 divided by 20. That will give us 0.00, 0.002. So 0.002 is the value for each small box on the vertical axis. So what we are going to do is we divide everything here by 0.02. We divide everything here by 0.002, as I've been doing in the other videos. So let's go straight to the point to plot our graph. So we begin with this. When x over z was 0.112, this was this. How do we get this particular value on this graph? It is very, very difficult, but with this trick, it is good. We are good to go. So we say 0.112 divided by this. Let's try and see. So 0.112 divide by 0.002. That will give us 56. It means we have to count 56 small boxes, and then we get exactly this value. Or you may say, yeah, that is it. So we count, this is 10, this is 10, 20, 10, 20, 30, 40, 50, 55, 56. 56 is right here. Good. So 56 against what? 1.887 divided by 0.02, we have 1.887 divided by 0.02. What do we have? We have 94.35. We round it down. So count 94 small boxes on this axis. So this is 10, 20, 30, 40, 50, 60, 70, 80, 94 is here. So this is 94. Good. So we put a straight our ruler here so that we don't mix it up. And then we trace this line. Good. This is where they intersect. And that is the first point. We do it for the second. We have 0.105 divide by the value for each small box 0.002. We have 52. You round it up, 52.5. That is 53. We're going to count 53 small boxes here. So this is 10. This is 10, 20, 30, 40, 50, 50, 51, 52. 52 is right here. So what do we have here? We have 1.429 divide by 0.02. We have 71.45. You round it down. So we're going to count 71 small boxes on this line. This is 10, 20, 30, 40, 50, 60, 70. 71 is right here. This is 71. So this is 53. You put this line, this ruler here, so that you don't miss out the line. And then this is 71. You trace it up here. Good. This is the point of intersection. And that is the second point. So we are going to do this for all the values. And we are done with the graph. This is 1, 2, 3, 4, 5. These are your points. You have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the next thing we want to do is to draw our line of best fit. This is the reason why I always tell us to use a transparent ruler. You see this? If it had an opaque ruler, you won't see these points as they are appearing here. So we go for our line of best fit. In every experiment, there's always a black sheep value, and here you can see that this is my black sheep value here. Your line of best fit must touch at least 3 lines, and here we have 4 lines, 4 points on the lines. It's touching 4 points, 1, 2, 3, 4. This is not too good, just only 2 points. We can't go with this one. We can't go with this. So we go with this. We go with this 4 points. Good. Good. This is our line of best fit. Exactly what I was predicting. So in any case, we have the first graph as the graph I predicted. Good. So the next thing to do is to draw a triangle. The triangle must be very, very big. When it is big, you minimize error in the experiment. So we choose this point. This point is good. We also choose this point. Sorry, this point. This point is also good. And then we trace it down here. This point is also good. See what I'm doing? This point, and then this point. So let's join it together. We have this, and then you extend it down with broken lines. Good. You join this one here, and then you extend it here with broken lines. Good. You also extend it down here with broken lines. and then you extend the topmost one here. With broken lines. Good. So these are the broken lines. So here is your change in x over z, and here is your change in t. Permitted to find the graph here. The slope. So the slope of the graph is change in x over z divided by change in t. This point here is your x over z2, and this point here is your x over z1. This point here is your t2, and this point here is your t1. So let's get this value straight. This particular point here is 0.12. So this is the same thing as x over z2 minus x over z1 divided by t2 minus t1. If you do that correctly, your x over z2 is 0.12 minus your x over z, which is 1, which is this point. How do you get it? Make use of your small value for each small box. So you have 0.002 times 10, 20, 10, 20, 30. This is 35 times 35. We have 0.07, so minus 0.07 divided by this point. What do you have here? This is your T2. 0.02 times 10, 20, 30, 40, 50, 60, 70, 80, 90 times 95 times 95. You have 1.9, so this is 1.9 minus. What do you have here? We have 0.02 times, this is 10, 15, 16, 17, 18 times 18 times 18. That will give you 0.36. So you have 0.36. So your slope or your gradient is 0.12 minus 0.07. You have 0.05 divided by 1.9 minus 0.36. We have 1.54. We have 0.05 divided by 1.54. We have 0.032. Let's put it 40p. 25 approximately. Therefore, the slope of this graph is 0.0325. Don't forget that down here is per cm, and if it goes up, you're going to have cm. So this is the value for the slope of this graph. We are done with the graph. You may love to screenshot. This is it. Good. So we are done with this. We are also done with this. We are done with the slope. Let's evaluate this. They ask us, given that that is question ix, given that your S is equals to A all over P, and that your A is this, and that your A is 5.31 exponential negative 4 cm square, which that we should find P. So from here we make P the subject formula. So we'll have this this S over 1. So we'll have A is equals to SP, and this implies that our P is A all over S. So this implies that our P is equals to our A is 5.31 times 10 raised to negative 4 cm square divided by S, which is our slope. Our slope is 0.0325. 0.0325. Good. So we have 5.31 exponential negative 4 divided by 0.0325. That will give us 0.01634. Therefore, P, don't forget this is cm. Cm will cancel cm here, and you left with another cm here. So our P is equals to 0.01634 cm. That's the value for our P. The next thing they ask us to state precautions. Precautions are the things you do in the experiment to get accurate results. So in this experiment, it is alternative. You state this way. You don't state in group. We would. I would have ensured tight connection. That is one precaution. Precaution number 2. I would have avoided dragging the jockey along the length of the line CB. You drag the jockey on the line, you don't get accurate results, and there are also more other precautions that you can get. That is just 2. Just need to stage in just 2. The next thing they ask us is to draw a graph to show the relationship between the resistance and the temperature of length of dependent resistor. This is basic electronics. In current electricity, when the resistance of the wire, when the temperature increases, the resistance of the wire also increases. So we are answering question number B now. So what I mean here is that the temperature of the wire is directly proportional to the resistance of the wire. But in basic electronics, the resistance of the wire is inversely proportional to the temperature of the wire. Meaning, increase in the temperature will cause the resistance to decrease and vice versa. So the graph will look like this. For a light dependent resistor, the graph will look like this. And this is for our resistance in ohm, 0,0, and then our temperature in degrees Celsius. So this is what you will have. So you have something like this. The graph will look like the graph for half-life, something like this. This is what you have. Good. So that here we have like 8 degrees Celsius. At 8 degrees Celsius, the resistance is just 2 ohm. Increase in the temperature will cause the resistance to decrease and decrease. This is the graph they asked us to plot. We're also asked to find, which is the last question, that is BII, the equivalent resistance in this circuit. The first thing you do here, have to redraw the circuit. You know that these 2 resistors, they are in series and they're in parallel with this and this. So you draw a circuit like this. This is the terminal P and that line here, and then this is the other resistor of 6 ohm, and this is the junction, and this is terminal Q. We have this junction here, another junction here, then this down here. So this resistor and this are in series, so we can just put one straight line here for to represent the four of them, the two of them. 4 plus 6 will give you 10. This is 10 ohm, and this resistor that is put diagonally also means something like this. So we can easily put something like this, and this is the arrangement. So this is also 10 ohm. So the equivalent resistance now becomes 1 all over R is equal to 1 all over 6 plus 1 all over 10 plus 1 all over 10. You find the LCM. The LCM is 6 times 10 times 10. That will give you something 600. So this 600 into 6 will give you 100. And this into 10 will give you 60. This into 10 will also give you 60. So if you do that correctly, you have 100 plus 60 plus 60. That will give you 100 plus 60. Sorry, 100 plus 60 plus 60. That will give you 220 over 600. 1 all over R. So you reciprocate this. So your R becomes 600 divided by 2 to this. This go, you have 60 over 2. So 60 divided by 2. That will give us, so therefore R is equal to 2.727 ohm is the combined or the equivalent resistance in this circuit. I stand to be corrected. If anybody have a contrary view to this, you may drop your answer in the comment box. To this, we have come to the end of this video. Thank you, my Liberian friend. God bless you. I wish you guys success in your exams over there. Don't forget to subscribe, like, comment, and share this video. Thank you. God bless you. Bye-bye.